Hey guys, welcome back to chemistry, second semester final exam study guide. So this video's purpose is last year I made tutorial videos where I walked through every single unit on the study guide and I solved all the questions together with you guys. But that was for 2023, and for the 2024 school year, the Zionsville chemistry department added a lot of key concepts that I did not cover on that video last year. So this video serves the purpose of answering some of the questions that I did not answer on that study guide because they weren't there last year. So if you guys go through your study guide based on the videos from last year that I made, you'll notice some of the questions that my study guide from 2023 are, it's not on there. So these questions are there for you guys so that I at least go over some of this stuff with you so you know what you're doing for your final. Let's get started. I always start with the equations. I review every single equation you're given. That I call unit 0 because equations are where you start for all these calculations. You need your equations to solve the FRQ portion of your examination. So getting started with the first equation you're given here, that is P1V1, that is your combined gas law. So you're going to have pressure, volume, temperature, and moles. You won't see moles very often, but you might. That's N, so just keep that in mind. And you're going to be setting this in proportions, so just make sure how to do that algebraically. That is the combined gas law. Next up, we have PVNRT. That is going to be your ideal gas law, where R is a constant. It's given there. Just remember that you're going to be given R. Don't try to just randomly solve for R unless it tells you to do so. Yeah, just keep that in mind. Next one, we have Dalton's law of partial pressures. It's saying that the total pressure of a container is going to be the sum of each individual gas's pressures. Pretty simple to use. Next up, we have the mole-Rho conversion factors. We have 1 mole in particles, we have the moles to liters, and moles to molar mass. Remember that the molar mass is going to be in grams per mole, and this number comes from your periodic table. So it comes from periodic table. Alright, horrible spelling, but periodic table, right? You're going to always use that. Remember, I drilled this into you, so grams per mole, keep that in mind. And then we have analytical stuff with percent yield and percent error. So we're going to have for percent yield, it's going to be your experimental over theoretical times 100. And then for percent error, it's going to be experimental minus theoretical over theoretical times 100. And that's going to be in the absolute value form for the experimental minus theoretical for percent error. That just means that whatever number you get as a percentage, if there's a negative attached to that percentage, just ignore that negative and you'll be fine. That's all it's saying. Next up, we have molarity and molality, capital M and lowercase m. Do not confuse those in your test. They're there to trick you. You won't see molality very often. Moles per liter, of course, molarity for concentration. Molality, moles of solute per kilogram of solvent. Remember that stuff as well. And then we have one of my most favorite equations, delta T equals IKM. This is used to solve for your colligative properties. So you're going to be solving your boiling point elevation and freezing point depression with these equations. Just remember that the K can be the freezing or boiling. The I in this equation is your Van't Hoff factor. I always misspell this guy's name. I believe it's apostrophe goes here. Van't Hoff factor. Let me see that real quick. Factor. Remember, covalent compounds have 1 for that. Ionic compounds, it's the degree of dissociation of its ions. You'll probably see that more often in my previous videos in that respective unit, but just a quick review. And then lowercase m, of course, it's molality, so keep that in mind. M1V1 equals M2V2, the classic dilution equation where M is molarity, even I'm getting confused, molarity, and V is volume. right? So as long as your volume's in the same unit for V1 and V2, you can use either milliliters or liters. Just make sure, keep that in mind. You can't just go use liters and milliliters at the same time. They have to be the same unit. All right, and my favorite equation as well, Q equals mc delta T, right? Q equals mc delta T. That is your thermodynamics or thermochemistry equations to calculate heat, which is Q. This is for the phase changes. And then this is your Gibbs free energy calculation. Remember, S is entropy, temperature, delta H is enthalpy, and yeah. Then we have the pH calculations. pH is negative log of the concentration of your H plus ions. pOH is the negative log of the concentration of your OH minus ions. That, of course, you should all know by now. You can go back and forth from the H plus concentration to the pH by using the log. It's just log math. If you're in calculus or pre-calculus, you should probably know this well. It's very simple log math. Your calculator would do it all for you. You just need to know these formulas. And there's the same for pH and pOH. Same for H plus and OH minus. You just got to know how to use them. Remember that when you raise it to the power, there's a negative in front of that. So when you raise it to 10 to the xth power, right, that x is going to be 10 to the negative xth power, right? And the sum of the pH and pOH will be 14. Remember that if your pH is less than 7, it is acidic, and if your pH is greater than 7, it is going to be basic. So that's basically the really quick and rushed rundown of your equations. Yeah, so let's get started with unit 1, right? Get this over with. All right. Unit 1 is the states of matter and gas laws. There was one question that I did not answer on that last year's video, and so let's go over it now. Define the following: freezing, melting, boiling, condensing, sublimation, deposition, evaporation, and STP. So we all know that freezing is when we go from, let me just write this to the side, freezing. We're gonna, freezing is we're gonna go from liquid to solid. Right, and so that is going to be freezing. Melting is going to be, and we'll talk more about this in thermochem later on. We're going to talk about endothermic and exothermic, so I'm not going to mention that too much right now. So this melting, we're going to go from solid to liquid, right? Boiling, we're going to go from liquid to gas. Condensing, we're going to go backwards. Condensing, we're going to go from gas to liquid. Sublimation, that's a big word. Sublimation, did I even spell that correctly? Yes, I did. Sublimation, we're going to go directly from solid to gas. Deposition is backwards. Deposition, we're going to go from gas to solid. Evaporation, this is a key concept. Let me actually move it over to the side here a little bit. So evaporation is a funny concept, right? And you guys talk more about this in AP chemistry if you decide to take it. But evaporation is interesting because say you have a liquid in a container, right? That's a beaker, and you have a container, and your solute is what's it called? Or salt, like the liquid solution is going to be evaporating, right? And a certain level of particles reaches into that and exerts a pressure, right? And once that pressure reaches equilibrium, that pressure will directly impact, so that this pressure is called vapor pressure, right? And so when your vapor pressure is in equilibrium with the amount of evaporation occurring, then you're going to have equilibrium. And then that's just saying that you're evaporating as much as you're unevaporating the liquid. And it kind of doesn't make sense if you hear it this way, but it's a strange concept, and I recommend that you go back into your notes actually and look at evaporation as part of your gas laws. Just you do need to know vapor pressure, and you need to know equilibrium relating to evaporation. So just keep those in mind. And then of course we have my favorite, standard temperature and pressure. Standard temperature and pressure. I have to write this all out because it's a review guide. But standard temp, pressure. And standard temperature and pressure, you're going to be at, you're going to be at 0 degrees Celsius, which is 273 Kelvin, and 1 atmospheres. Right. And keep that in mind. A lot of people get it confused with room temperature, which is 25 degrees Celsius. So if someone asks you about room temperature, that's not STP. Room temperature is considered 25 degrees Celsius, which is 298 Kelvin. So just keep that in mind. Remember, just draw a line in between that. Don't get it confused. Standard temperature is different than room temperature. So yeah. Okay, so let's go ahead with Unit 4, Solutions. There's one question in Unit 4 that I did not answer from last year's video, and it's just another defining one. How boring, huh? Alright, so solute, solvent, and all that jazz. So go ahead and write it up top. Alright, so solute is going to be the stuff you dissolve, right? And solvent is the stuff that is dissolving the stuff you did. Okay, so it's confusing already. So let's just write it out. Solute. That is the stuff / substance you're dissolving. You put in to dissolve. Right? That's the solute. Solvent is the stuff actually doing the dissolving. Stuff doing the dissolving. So stuff doing the actual dissolving. And this together makes a solution. We have to talk about unsaturated and saturated. So unsaturated, easy way to describe this is, say you have a beaker with the water, right? Like just plain old water. And we're going to assume that that amount of water that you have in the beaker can only hold 100 grams of salt, like table salt, sodium chloride. So anywhere between 0 and 99.99999, right before you hit the maximum amount of solid dissolvable, which we said was 100, that is going to be unsaturated. So an easy way to define this is can dissolve more solute. And then when you hit your 100, exactly 100, no more no less, you're going to have fully dissolved to capacity. And then supersaturated, of course, you're forcing it, solution or solvent, forcing solvent to dissolve more than it can take, more than capacity. That is going to be your supersaturated. Colligative properties, you need to know boiling point. Let's just write this out as well. Colligative properties. Colligative properties, my favorite. You're going to have boiling point elevation. Boiling point elevation. And this is going to be where the more stuff you put in, more solute, higher temperature to dissolve. Or boil is what I meant. Right? It's kind of logical, right? The more stuff you put in the solution, the more energy you're going to need to boil that solution. That's boiling point elevation. Alright, let's talk about freezing point depression. Actually, just kidding. We're talking about vapor pressure elevation first. Vapor pressure elevation. That's VPE. Or sorry, I'm going crazy. Vapor pressure depression is what it is. Alright, so that's basically saying that the more solute you put in, The more solute you put in, the lower the pressure will be, the lower the vapor pressure. And remember what we talked about, evaporation and vapor pressure. That's the amount of pressure exerted back onto the solution, right? The more solute you put in, the harder it's going to become evaporated. So the vapor pressure will be lowered. Last but not least, we have freezing point depression. Freezing point depression, FPD. That's just saying that the more solute you put in, the lower the temperature you need to freeze. And this is the same concept as boiling point elevation, right? The more stuff you have in it, the more energy you're going to need to take out of the substance or solution or solvent in order to actually freeze the thing, because you have more solute in it, you have more stuff in it to freeze, so you're going to need more energy removed to freeze that solution. That's your colligative properties. It's not bad. It's just memorization. If you understand like the concepts of solutions and how that works, you're probably going to be fine for the test. Yeah, so last but not least, we have to talk about concentrated versus dilute. Concentrated vs dilute. Right, concentrated, you're going to have more solute per solvent. Right, higher molarity. And for dilute, you're going to have less solvent, or solute per solvent. Consequently, your molarity will be lower. Remember that dealing with concentration, you're going to be using units in molarity. Molarity. Capital M for concentration. Alright, just keep that in mind for concentration and you'll be all set. Alright, that covers that question. And let's go on to thermochemistry. Alright, so define the following: endothermic and exothermic, right? Easy way to remember this: endothermic, heat enters the system. Let's do this in purple. Endothermic, heat enters system. And exothermic, heat will exit the system. Heat exits system. Okay, that S is horrible. I gotta rewrite it. Okay. So for the sign of each, endothermic will be positive because you're entering heat in. So endothermic is positive. Exothermic, you're releasing heat, so it has to be negative. It's just a memorization thing. For specific heat, that is the amount of heat required, amount of heat needed to increase temperature by 1 whole unit per mass unit of a substance. So it's the amount of heat it needs to raise the temperature by 1 whole number unit per mass of a unit of a substance. Next up, phase change, endothermic versus exothermic. It can be summarized into quick diagrams here. If you go from solid to liquid to gas, this is going to be endothermic. Right, you're increasing heat in order to make it into a gas. If you go backwards to gas to liquid to solid, this is going to be exothermic. Right, you're releasing heat to become a lower energized state of phase, is what you'd say. CI says, does temperature change during a phase change? And the answer to that is no, with 4 exclamation marks. No, 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 no. Temperature does not change during a phase change. because that's the moment. It's that's when your potential energy changes, so it will not have the temperature change. No slope is what I wanted to say. No slope. Last but not least, we have enthalpy for phase changes, where delta H fusion equals delta H solid, or solidification. And then we have delta H vaporization, and then delta H condensation. So in this case, delta H fusion refers to the solid to liquid, right? Solid to liquid. So then the this will be positive. It's endothermic, as we mentioned here. Next up, we have delta H solidification, where we go from liquid to solid, which will be negative. As we go liquid to solid, it is exothermic. Same logic, delta H vaporization, we go from a liquid to a gas, which of course is endothermic, positive. Delta H, delta H condensation, right? Going from gas back to liquid, which is negative, because we talked about how it is exothermic. So that is Unit 5 of Thermochemistry. That's the only question that was neglected off of that unit. So moving forth down to Unit 6, which is rate laws, or more officially, reaction rates. There's a crap ton of terms I gotta define here, so hold on if you will, and let me get through these real quick. So it says define the following: activation energy, activated complex, yada 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 yada. Okay, so let's get started here. There's a rate law question down here, so I have to like be aware of space as well. Why don't we move this out here, and we'll just define it here. How's that? Okay, so activation energy is the active energy. So activation energy is the energy needed to start chemical reaction. Right? That's the amount of energy you need to start the chemical reaction. The reaction does not start unless that activation energy is provided to its fullest extent. So think about lighting a Bunsen burner, right? That methane gas off of the tap, that's still coming out. But what do you need? You need is that activation energy provided by the spark with your flint and steel, right? Without that activation energy provided by the spark of the flint and steel, you're never going to get that fire to light, methane to light on fire. So that's a good example of activation energy. Yeah. And then we have activated complex, right? Activated complex is going to be, I have to write this out, give me a second. Activated complex. Okay. Activated complex is at the top of your chemical reaction, like the curve, right? This is where your products are first formed. The point, we'll call it the point at which the reactants turn into products. And this is at the top of the curve. Highest point on curve is what I want to say. That is the activated complex. Next up, we have the rate of reaction. Rate of reaction. And the rate of reaction is simple. It's a very simple concept. It's a measure of the change in the concentration of your disappearance and appearance. So in elaboration, that's measures the rate at which the concentration of your reactants disappear, or your concentration of the products appear. And that is rate law, or rate of reaction. It's just measuring the rate at which your concentration of reactants and products disappears and appears respectively. Elementary steps, these are simple to understand. Elementary steps are going to be individual reactions that kind of sum up the overall reaction, right? So individual reactions that occur prior to the overall reaction. So it's just the reactions that kind of have to lead up to the overall reaction. That is what elementary steps would be. And then intermediates, give me a second to write this. Intermediates are going to be substances that are made in the reaction and used up while reaction proceeds. So this stuff is like if you make like a byproduct, but that byproduct is then used to drive that overall reaction to completion, that is an intermediate. So say you have like the synthesis of like some random compound, and you're making hydrogen in between of it, but then immediately after that you use that same hydrogen to make water in order to get to that mysterious compound. I don't even know what it is. That is going to be the intermediate, because you're using that, you're making it and then using it immediately to get to the final product. It's like a gateway. The gateway compounds, as you would call them. So that's intermediates. And then we have Gibbs free energy, right? Gotta scroll down even more. Gibbs free energy. Gibbs free energy is delta G. That's what you would call it. That looks like an A. That's not good. Delta G. That tells you the spontaneity of something. Spontaneity of substance. If delta G is less than 0, which means if it's negative, it's spontaneous. It's spontaneous. If delta G is greater than 0, not spontaneous. And another way for to say to mention spontaneity is going to be thermodynamic favorability, right? So if it's spontaneous, it is thermodynamically favored. If it's not spontaneous, it is not thermodynamically favored. Enthalpy and entropy, I hope you know this by now, but enthalpy is delta H. That's the change in heat, is what you would say. Change in heat. Like the change in internal heat. And then entropy is delta S. And this is the degree of randomness. Degree of randomness, the substance or anything it holds. So entropy is like the chaos, right? The degree of chaos. And then last but not least, we have spontaneous reactions. We kind of talked about this with Gibbs free energy, but spontaneous reactions, Spontaneous reactions are going to be like delta G is negative, and is thermodynamically favored. Big words, but that's just saying that it it tends to occur more naturally in the natural state rather than you having to force it by plugging in other extraneous sources of energy to make that equation or chemical reaction happen. So that's just what it means by spontaneous reactions. Alright, so that's that. And then continuing on with the Unit 6 reaction rates, we have evaluations of increases and decreases in entropy, right? So for entropy, so I think we have space to just straight up write on here. Do it in my favorite color, purple here. So if you heat water from 0 to 20 degrees Celsius, right, you're increasing, hold on, I might have to erase this stuff. It's lagging. Okay, so I'm just gonna grab this eraser and erase this stuff. There we go. Right? Alright. We have increases and decreases in entropy, right? So we have here, if we heat water from 0 to 20 degrees Celsius, we're increasing the movement of the molecules of water, right? From frozen to liquid state, we're increasing the amount of movement that occurs, which means that there's an innate increase in chaos. That means there is an increase in entropy. Next, we have a decomposition reaction. A decomposition reaction is where one molecule splits into its respective components. That separates into two parts, which is two separate molecules, which are innately have more entropy. So you're increasing the degree of entropy in this as well. Next, we have a gas condensing into a liquid, right? If you're going from a gas to a liquid, you're going to have a decrease in entropy because this is from going to gas to a liquid. This is an exothermic process, and you're going to be releasing all that energy, and so you're going to be less chaotic in movement in the particles associated with the substance. Therefore, it will be a decrease in entropy. And last but not least, we have a solid dissolving in water. This is an increase in entropy, and let me explain why. If you have a solid solute that dissolves in the water, a liquid solvent, your solid solute had less movement as a solid form, but now it's dissolved in water, which means that it takes into account the properties of the liquid water, which means that it's going to be moving more chaotic than before, so you're increasing entropy. Alright, question 6 says, given the following data, you're going to be determining the rate law. This is an FRQ question, and it's good to know how to solve these questions, which I'll show you. I have not solved this beforehand, so we'll see how this goes. So we have A plus B yields C, right? And so the goal to this is to find the experiment where A changes but B stays constant. So for example here, experiment 1 and 2, A changes from 0.015 to 0.03, but B remains constant at 0.01. That is the thing you want to use. That's what you want to use to figure out for A. So if we have A, we're going to set this, the higher number goes on top, 0.015 goes on the bottom, and we're going to set that as X. And this format is the same for all rate laws, so you just have to memorize this or write it down somewhere and, brain dump this before the exam. So whatever number corresponding with 0.03, we're just going to put on top as well. 3.4 times 10 to the negative 4th on top, and 8.5 times 10 to the negative 5 on the bottom. When we divide this, if we divide 0.03 by 0.015, we're going to get 2. 2x equals and then we divide 3.4 times 10 to the negative 4th by 8.5 times 10 to the negative 5, when we get 4. So x here, if you raise 2 to the second power, you get 4, right? 2 times 2 is 4. If you raise 2 by the second power, it's 4. Therefore, x is 2. So this is second order for A. In the same way, we can calculate for B as well. We want something where it changes for B but remains constant in A. Remember, the higher number also goes on top. So we have 0.04 over 0.01. This is experiment 2 and 3, because B changes from 0.04 to 0.01, but A remains constant at 0.015. So this one we're going to set to Y. And remember, the higher number concentrated B, the rate law, we're just going to put on top. So 3.4 times 10 to the 4th over 8.5 times 10 to the negative 5. Right? And so if we divide 0.04 by 0.01, we're going to get 4. 4y equals, and this is 4. This is the same numbers from the previous, so we can just carry that over because we know it's 4. So in this case, y equals 1. So that's first order for B, because if we raise 4 to the first power, you're still going to get 4. So the rate law for this is you just take into account both of these. So it's second order for A and first order for B. So the rate law is always going to start with rate equals K, and then the concentration of A raised to the second power because it's second order, and B raised to the first power for because the concentration is first order. So that is your rate law. You don't really need that one there. It's nice to have. I mean, it's not nice, but if it makes you understand better, go ahead and keep it on there. But I'm gonna take it off because it's understood that it's just 1. The overall order for this reaction is calculated by adding up all of its respective orders. So we had order 2, second order for A, and first order for B. So 2 plus 1 is 3, and therefore it's third order overall. Alright, and last but not least, we have to solve for K. So in order to do this, we literally just grab this equation, choose an experiment, and just plug it in. So we're just going to take into account the first experiment, because I always do the first experiment. It's just the first one down the list. So we have rate equals K times A squared times B. So rate in this case is 3.4 times 10 to the negative 4th equals K times the concentration of A, 0.03, remember that's this number right there, 0.03, squared times 0.01 for concentration of B. So when we solve this, 0.03 squared times 0.01 will give you this number here, 3. So if we write this again, 3.4 times 10 to the negative 4th equals K times 9 times 10 to the negative 6. So if we divide this by 9 times 10 to the negative 6, we're going to get K. And in this case, K will be 3.4 times 10 to the negative 4th divided by 9 times that, and your K will be 37.777. We're just going to round that to 37.78. There's no unit for K because it's a constant, and that is your K value for this scenario. Alright, moving on, scrolling just a little bit here to make room for that delta G question here. So we have a reaction has a delta H of 37.1 kilojoules per mole and a delta S of 106.8 joules per kilomole, or Kelvin times mole. Would this reaction be spontaneous at 250 degrees Celsius? So all we have to do in this scenario is literally plug and chug. So we have delta G equals delta H minus T delta S. In this case, delta G we're finding equals delta H is 37.1 minus T temperature. This has to be in kelvins, so plus 273 will give you 523 Kelvin. So 523 times the delta S, the entropy, 106.8, right? So 523 times 106.8 is a very big number. 37.1 minus 55,856.4, right? 37.1 minus that will give you delta G equals negative 55,819.3. And of course, that delta G value is negative, so therefore this reaction is spontaneous. Because delta G is negative. It is thermodynamically favored and therefore spontaneous. Last but not least, we have Unit 8 for acids and bases. This is the last question we're going to go over. So we're going to define what a Bronsted-Lowry acid and base is. It doesn't say define the acid, but we're going to go ahead and define the base and acid anyways. So a Bronsted-Lowry acid is going to be the H plus donator. And the Bronsted-Lowry base is going to be the H plus receiver. Right? So if your acid is HCl, right? So that H plus is going to be donated to the base. Donated to base. And the base will receive the H plus ions from the acid. And that is the very simple definition of a Bronsted-Lowry acid and base. That wraps it up for all of the questions that were neglected due to the changing curriculum for the 2024 final exam study guide for second semester for chemistry. I hope this helped. Leave questions in the comments and I'll try my best to answer them. And good luck on your finals. Thanks for watching.